Okay, everybody. It's time for us to begin our main presentation for the evening. I want to welcome everybody who is tuning in via our YouTube webcast. Welcome you to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. Tonight is all about stars. For most of human history, we viewed stars as things that are eternal, everlasting, and unchanging. They were part of this firmament, and they were made of some ethereal substance that was unlike anything found on Earth. That view began to change in 1572, when suddenly a new star appeared in the sky, and it shone as brightly as the planet Venus. Now, today we know that that wasn't actually a new star being born. It was an old star that was dying in a supernova explosion. But the point is, it showed us that the heavens do actually change, that stars can appear and disappear. Now, with the birth of the telescope, astronomers began to see that stars weren't the only things out there. There were a lot of areas where stars seemed to be associated with patches of something that they called a shining fluid, and otherwise known as a nebula. They named them nebulas after the Latin word for cloud. And in the 1800s, astronomer John Herschel was the first to propose that perhaps this shining fluid could actually condense gradually and go from a diffuse nebula to a denser nebula to one or several stars, nebulous stars, and then eventually to just a single star or a group of stars with no nebula around them. Now, this broad brush picture is actually essentially how we believe today that star formation happens. But the devil is in the details. We still have a lot of questions that we want to answer, like where exactly do stars form? Why do they form there? What determines how massive they're going to be? There are many, many questions to keep astronomers busy for decades to come. Tonight's speaker, Kara Battersby, is a postdoctoral fellow who studies star formation with the Submillimeter Array, or SMA, which is a Smithsonian telescope that's located on top of Mauna Kea in Hawaii. She leads a survey that is looking at star formation in the center of our galaxy, which is called, let me get this right, the SMA Legacy Survey of the Central Molecular Zone. And tonight she's going to explain why the rule breakers of the Galactic Center have turned it into the Wild West of star formation. Please welcome tonight's speaker. Did I get your name right?
Hi, everybody. I can't tell you how honored I am to be here and to have so many people come to hear me talk. This never happens at astronomy conferences. This is amazing. Thank you so much for coming. I want to give a special shout out to everyone in Pratt right now who's watching via live stream, especially the talented and gifted Latino program who I got to meet before at the talk. Now, I've given a lot of talks throughout my career as an astronomer, but this is also the first talk that my mom and dad, my best friend Buffy have ever come to, so I'm super excited that they're here. So thank you so much for coming today. So I'm going to talk to you guys today about the Wild West of star formation. So when we talk about the Wild West, think about outlaws and rule breakers and nothing really matters and just do whatever you want to do and everything is just really crazy. Now star formation, on the other hand, star formation is the process of just this diffuse space in between the stars. So in between the stars in our galaxy, you have a whole bunch of gas and dust, but it's very, very, very tenuous. Actually, the space in between the stars has a density that is about the same as the best vacuum we can create on Earth. So that's how little stuff that there is in between the stars. Same as the vacuum, best vacuum on Earth that we can create. And but in between the stars, all that stuff can actually come together under the force of gravity, somehow miraculously in the sun, which is much, much, much denser, and they can come together and they can form stars. And so I'm going to talk about the Wild West of star formation, which is a region where, we like to think star formation obeys some kind of rules because it allows us to understand it throughout the entire universe. But there's certain rule breakers, and we want to understand what's happening there. And so we're going to explore the wild west of star formation. So as Christine said, this talk is going to be all about stars. So hopefully you guys are on board with stars. If not, I'm going to explain a few quick things about stars. So this is a picture of our closest star, the sun. And actually here is a video of the sun just yesterday. And so this is an iron line. This is from the Solar Dynamics Observatory. So you can go online and download a video of the sun in different wavelengths at any time that you want. So we also thought of the sun previously as just this perfect magical sphere in the sky. But as you can see, it has a lot going on. It's very complicated. So what makes a star is that in the center of it, it actually is able to produce, by fusion, produce energy. Fusion is the process of particles moving together so quickly that they can actually collide and become one particle. So most times, usually this is something like hydrogen. So hydrogen is just, in this case, it's totally ionized. There's no electron. It's just the proton. So you have two protons, and they're going to come together. But usually there's the electromagnetic force, and they would want to avoid each other. They don't want to get anywhere near each other. There's a really strong force. But if you move it around fast enough, you can actually get these things to collide. And then when they do collide, they stick together, and they produce a ton of energy. So this is nuclear fusion, and that's what powers stars. So any object that can get enough mass together and move particles quickly enough that they can produce fusion, that is what makes it a star. Okay, so this is our closest star, but as you all know, there are many, many, many more stars in the galaxy. At least 20 or 30 or many, many more. So that's sort of what you might think. That's what you might think in Boston at night sometimes. There's only 20 or 30 stars. But looking at this beautiful picture here of our Milky Way plane over this lake here, you can see, so this is actually the plane of our Milky Way. So we're in a galaxy, and we're looking through the plane of the galaxy. And so we can see the plane of the galaxy here. So there are about 100 billion stars in the galaxy. Kind of can't even really imagine what that number is. I think I was told it's like the number of grains of sand on Earth, which is a lot. All the beaches, all the grains of sand, that's a lot of stars. But we're not the only galaxy. There's a lot of other galaxies. This is Andromeda, our closest spiral galaxy. This is M51, a beautiful face-on grand design spiral galaxy. And M101, the pinwheel galaxy. So there are many galaxies throughout the universe, and each of these galaxies has tens of billions, hundreds of billions, sometimes more stars than that. And beyond that, the entire universe is just filled with galaxies. So this is from the Hubble Space Telescope, an image where basically the Hubble telescope, which is this really, really sensitive, amazing space telescope that looks at visible light, just stared at a blank patch of sky for a really long time. A place where we thought nothing at all was there, and just stared at it, kept adding up all the photons, kept adding it all up. To give you some perspective, it's approximately, this is the area that it covered. So it's actually a really small part of the fraction of the sky. So here's the size of the moon, and here's the deep field that you're looking at. So if you can imagine how many moons it would take to fill up the entire sky, and then how many of those little fields it would take to fill up the entire sky, that gives you some idea of how many galaxies are in the universe. Because each single smudge, each dot, each little blip, each of these things is a galaxy. So this image contains about 15,000 galaxies. It's really totally mind-boggling. And then inside of each of those galaxies is like 100 billion stars. So if you guys aren't sold on stars being important yet, I don't know what to do. Stars are really the building blocks of these galaxies. And this is just to give you some sense of how big the universe really is. So one of the fundamental pursuits of humankind, and I would say also of the astronomical inquiry, is the question of where do we come from? So I'm not talking about where do we come from, like where do babies come from? I'm talking about where do we come from in a really global sense as humankind. So as Carl Sagan once said, if you want to create an apple pie from scratch, first you have to invent the universe. So if you want to create human beings, first you have to invent the universe. So this is our cosmic history of the entire universe. We're here in the present day, right here. This is time along this axis, and this is the Big Bang, so the very beginning of the universe. And you can see lots of different things have happened over time, and all of these things that have happened have been important in creating who we are today. All of them have played a role in building the elements and molecules that make us up as human beings. To explain that a little more clearly, you guys have all hopefully seen the periodic table before. Shown in green are all the common elements in the human body, and it doesn't look like the blue turned out very well, but blue is trace elements, and that's these elements in here. But so these are the most common elements in the human body. So where did all these elements come from? Well, hydrogen and helium came from the Big Bang. Those came in the very beginning of the universe. That's when those were created. What about all these other elements, though? These were all actually formed inside of stars, every single one of those. So carbon, nitrogen, oxygen, all of those are formed inside of stars. Everything past iron was formed in a supernova explosion. So this is really profound if you think about it. So basically what happens is inside of a star, you fuse all these elements together, these elements fuse, and eventually at some point, the star dies and explodes, and it spews all those new elements out into this space in between the stars. And all this gas and dust and all that stuff slowly, eventually over time, recollects and forms a new star. And it forms a planetary system around that. And maybe if you're lucky, that planetary system will form life, like us. So Carl Sagan famously said, "We're made of star stuff. We are a way for the cosmos to know ourselves." And this is a picture of a supernova. So you want to think about being connected to the universe, being a part of the universe. You couldn't be you without having all these stars form and die and explode and to create the elements that make us, each and every one of us. So 90% of your mass comes from the insides of stars. Okay, so we're really interested in stars. And as Christine said, some of the questions that we like to ask are, how and where do stars form? How often do they form? What are the important physical mechanisms? What kind of physics is taking place and determines whether or not stars can form? Where can they form and where can't they? What about the environment? What kind of environment is required for star formation to happen? And to put this more simply, what are the rules for star formation? And who is breaking them? That's the big question. Okay, so I'm going to zoom in on, this is constellation Orion is where we're going to start with this video. So you guys are all familiar with the 3 belt stars and Betelgeuse and then Rigel down over here. So now we're zooming in to the Orion Nebula. So the Orion Nebula is the closest place for massive star formation. As you can probably guess, we're not actually zooming, we're not traveling at light speed through space. This is just a fancy cinematic effect. Now we're just zooming in on a small little star forming in this little tiny cocoon. Okay, so this now is a Hubble image. Sounds so quiet now without the music. This now is a Hubble image of the Orion Nebula. And this is just to give you a sense of what the anatomy of a star forming region looks like. So this is a visible light image. And so you can see lots of different features. So in the center here, you have a cluster of massive hot blue-white stars. You also have some hot ionized gas. You have this reflected starlight, and all this stuff back here, this is all dust, basically, in the nebula it's having scattering. The light that's being produced by the stars is being scattered off of the dust, and it's producing all these beautiful colors. Now, I don't know if you guys know what I mean when I say dust, but I remember when an astronomer first talked about dust to me, I was like, what is going on in space? Somebody needs to clean it up in there. It's got so much dust everywhere. It's not that kind of dust. It just means a bunch of molecules that are amalgamated together, and they're not really dense enough to be, a planet or an asteroid or anything like that. It's a very fluffy, just amalgamation of molecules. But we see it all over space. And we also have coal dust right here. So the coal dust is where we think that new stars are going to be forming. So in order for a star to form, you have to take all of this matter and push it all together into just an impossibly small space. And so if you have a really, really hot gas, which has a lot of thermal pressure, the gas is moving around a lot, it's going to be really hard to collapse it down and form a star. So stars form in the coal dust. So this stuff, the stars have already formed there. So the gas is no longer cold, it's blowing it all out, and it's now just in a visible cluster of stars. So the Orion Nebula is part of the Orion molecular cloud. So a molecular cloud is where stars form. I talked a little bit about how the space in between the stars, the density of material is about the same as the best vacuum that we can create on Earth. In a molecular cloud, it's about a couple, maybe 100 times more than that. So it's still not very dense. You wouldn't run into anything going through, you'd just be in space. I mean, they call it space for a reason. Okay. The temperatures of the molecular clouds are about 10 or 30 Kelvin above, so that's basically 10 to 30 degrees above absolute zero. And the density is about 1 times 10 to the 21 times less dense than water. So it's this many zeros. That's how many times less dense it is than water. So to just give you some sense of that. And most of the matter in star-forming clouds is in the form of molecules. So that can be molecular hydrogen, or actually carbon monoxide is a really common one. So you think carbon monoxide, maybe you think about carbon monoxide detector, carbon monoxide, oh no, what's going on? It's actually the second most abundant molecule in space, just carbon and oxygen, and so we use it a lot as astronomers. Okay, so I've talked a lot about star formation, but where stars are forming is also where planets are forming. So around these little zoom in pictures here, each one of these little stars has a protoplanetary disk around it. So it has a small disk of dust and gas that's around the forming star, and that's where newborn planets are going to form, in that disk around the star. That's a whole nother topic, for another lecture. I think you actually had one in March by Anjali. So I won't talk about that in too much detail, but clearly we care about planets as well, because we live on one and we're very biased. So to talk about star and planet formation, I spent a whole PhD thesis working on this, so to try to sum it up in one slide is sort of like sacrilege to me, but here are some of the basic terms that we use when we talk about star and planet formation, and these are all using real pictures. So this gives you some sense of what the process is like. So this is a galaxy, and within galaxies you have these giant molecular clouds, these big amalgamations of so they're actually really similar to clouds that we see in the sky. I mean, they're much different in terms of the actual densities, but the way that they look, they're kind of like wispy, and sometimes maybe you could imagine it kind of looks like a bunny rabbit or a turtle or something like that, but they have a lot of different shapes. I'll show you a movie of them in a minute. And within those clouds, you have some overdensities, some places where gravity is winning by just a little bit, and you have a little bit more material, and that's where the stars are going to form. That's where you have these protoclusters, this dense gas and dust. And this protocluster is going to go on to form a cluster of stars like you saw in Orion. And within this protocluster, you have these dense cores. So a core is shown here. That's the thing that's going to go on to form a single star. So it's a bunch of gas and dust together that's forming a big ball, but it hasn't collapsed down enough to actually have fusion. So it's still working on fusing, but it's not there yet. And around those cores, you have circumstellar disks, and that's where planets are eventually going to form. Okay, so here's sort of the life cycle of a star-forming region. So you start as a dense cloud of gas and dust, sort of slowly collapse because of conservation of angular momentum. As you collapse down, you're going to collapse into a disk, and that's eventually where the planets are going to form. So some of the physical processes that are important are basically all the stuff that's pushing outwards. So not every place in the entire galaxy is forming stars right now. Most places are not forming stars. It's sort of a rare process. So it has like very specific conditions, very specific things that need to happen. So you have the gas has a lot of pressure on its own. It has turbulent pressure, so it's just sort of moving around. You have thermal pressure, so as anything that has a temperature is moving around, so all of that energy, you can't just collapse it down. Magnetic fields can also inhibit star formation. So on the one hand, you have gas pressure, which is pushing out and saying, I don't want to be a star, I'm good. And on the other hand, you have gravity. So gravity is pulling inwards and wants it to become a star. So I used to think about this as sort of a fight between pressure and gravity, right? You're not going to win. I'm not going to become a star. You can't make me. But then I realized it's a lot more like, it's less of a fight, and it's more like, you guys have one of those friends who just really likes to give hugs. I'm probably am that friend. Sorry, Buffy. So, but one of those friends who just really likes to give hugs. That's gravity. Gravity is just like, can't we all just come together? Gravity is an attractive force. It just wants everything to come together. It's the attraction between any mass. So the sun, the moon, the galaxy, you, Justin Bieber, any of these things are all attracted to each other by gravity. So gravity's like, just give me a hug. Let's just be together and be a star. But the gas, on the other hand, is, I don't want a hug. I need my space. Give me some space. I don't want to form a star. And so in order for a star to form, gravity has to win out over the gas pressure. Okay, so just so you guys don't walk away thinking that this is what a star-forming region looks like, let me show you. This is a simulation from Matthew Bate that it's a computer simulation, so made on a computer, of a molecular cloud collapsing down and forming stars. So the color here is showing you the density of the gas. And you can see that the force of gravity slowly over time is getting stronger and stronger. And so basically the closer things are together, the more gravity acts. You'll start to see some small little white dots. Those are actual stars that are being formed. And sometimes dynamic interactions between the stars can cause one to go shooting off in another direction. You can see the star formation is finally picking up. You have lots and lots of white little dots here. Lots of stars forming. And eventually what would happen next in the simulation is you would have those stars would produce huge amounts of winds and radiation, and they'd eventually blow out all that gas and dust and stop the star formation process. Okay, well, this is a really beautiful simulation, but I'm an observer. I want to make my own movie of star formation happening. So I go to the telescope, and I look through the telescope. Actually, I'm a radio astronomer, so I'm more like I look through the telescope with my computer, and I take a picture of a star forming region. I just wait a couple minutes. All right, I'm going to take another picture. So I'm going to make a time lapse of star formation happening. This goes on for a little while, and it doesn't happen that way, though, because the whole process takes about 1 million years. So I didn't want to wait that long to do my PhD thesis, so I had to come up with a different strategy. That was a dramatization, by the way. I really didn't do that. I didn't sit at the telescope and take pictures every 5 minutes. They wouldn't let me do that. So the process takes about 1 million years. So the strategy that we take is, I can't actually make a movie of real star formation happening. I would love to do that, but we can't, unless you guys have 1 million years. Anyone? No? Okay, so what we do instead is we look at a lot of pictures of star forming regions, like this one here, and we try to pick out all the different evolutionary stages. This is a supernova remnant right here. This is winds around a young star that has just blown out a lot of material around it. These are some young stars here, and then this dark region here is actually cold dust, where new stars might form. And so you look at a lot of pictures and try to put together the sort of life cycle of star formation. It's similar to looking at a group of people and trying to understand what the life cycle of a human is. It's a little bit difficult. And if you only look at one group of people, you're probably not going to do a very good job. You have to look at a lot of people and try to piece together what their evolution would look like. That's sort of one of the things that we do in star formation. So to look at this cloud in a little bit more detail, so the picture is showing warm dust from the Spitzer and Herschel space telescopes. And so like I said, this is a supernova remnant over here. This is a very young star that's just forming an ionized bubble around it. So the star has just turned on, and it's just blown out this huge bubble around it. This stuff here, so you might actually think it's a hole in space, right? Should we report this? There's a big hole in space. Somebody forgot to put something there. It's actually not a hole in space. It's just the gas there and dust is so cold and so dense that it's just blocking the light behind it. It's like I just came up here and I'm just blocking the light so you can't see it, because I'm very dense as well. So that's what's happening here. So this is actually where the new stars are going to form, because that's where the gas pressure is least resistant to getting a big hug from gravity. So by looking at many of these different kind of images and studying them in a lot of quantitative detail, we can come up with an evolutionary picture that looks something like this. I'm not going to talk about this in a whole lot of detail. It was just my PhD thesis, no big deal. But so starless protocluster, little overdensities collapse down and form these cores. Those cores have outflows, and then they can continue to accrete stars while it radiates away some energy. Finally, it blows away all the gas and dust around it, and you have like a young embedded cluster. Okay, so going back to the Orion Nebula, I'm going to talk about another way that we can study star formation. So I'm just going to trim this down here so that we can zoom out. So now we're looking at sort of an optical infrared mashup, and now we're just going to look at an infrared image. So this is an infrared image from the Spitzer Space Telescope. So you can see that we're seeing a lot of different features here, and we're seeing a lot of young stars all along here. And so what we can do is we can actually go through and count up all those stars, those really, really young stars that are just forming. They're still cores. They haven't quite turned on nuclear fusion. And we can look at their properties and how many of them there are and properties of the cloud mass. And we want to do this to see if there's a rule for star formation. So this would be a rule for star formation. So we want to look at the number of young stars versus the mass of its birth cloud. So do you guys think that if you have a bigger cloud, you should form more stars or less stars? More stars, obviously. So this is the rule that we're looking for. We want to have more stars, more mass. So we look at all these clouds and right around us in the solar neighborhood and plot them up on this plot. And we see this beautiful correlation. Just kidding. So here's Orion A and Orion B, and there's really no correlation whatsoever. The mass of the birth cloud doesn't seem to be related to the number of young stars at all. But then had a revelation that it's not just the total mass of the cloud, it's the mass of the dense gas in the cloud. Because the fluffy stuff is not going to form any stars, it's only the dense stuff that's actually going to form stars. And so if you, instead of looking at just the mass of the birth cloud, you look at the mass above some critical density, then you get this beautiful correlation. Okay, here's a rule for star formation. Above a certain amount of density, if you look at the mass versus the number of young stars, you see this really nice trend. So looking at our star formation here, so we can see where the gravity and the gas pressure are working together. So gravity is sort of approximated by density. So gravity is a force on matter, and so if there's more matter, the gravity is going to be stronger. Whereas gas pressure, it can be turbulence, it can be thermal pressure, it can be magnetic fields. That's going to vary based on the environment. And so all of these clouds that we've been looking at are actually in really much the same environment. Here's a picture of our galaxy. We are here. So this is a photograph, right? Anyone? Breakthrough star shots, not done yet. And it's also not quite that good. You'd have to go for a lot longer than going to Alpha Centauri to get a picture like this. This is an artist rendition of our galaxy. So all the star formation regions that I showed you on that previous plot, so here we are, and here's the center of our galaxy. They're all right about there, in that tiny little circle. So there's a rule for star formation that we found there, but does that apply to the rest of the galaxy? Does it apply to the center of our galaxy? Moreover, does it apply to nearby galaxies? Does it apply to these galaxies in the very distant universe? Or is the rules for star formation very different there? So looking back at our star formation over cosmic time, actually the peak of star formation was in the very early universe. Only about 11 billion years ago is when the peak of star formation happened. So we're actually in a decline. The amount of stars forming in the universe is going down with time. And most of the stars that are in the universe right now formed about 11 billion years ago. And the conditions 11 billion years ago, a lot can change in 11 billion years. The environment is really different now than it was then. So if we want to know about star formation in a global sense, like not just in our own little neighborhood around the sun, but in all these different galaxies, we need to understand how it happened 11 billion years ago. But here we are, stuck at our Milky Way on this end, all by ourselves. Kind of a bummer. But there's this one really cool thing about our Milky Way, is that our Milky Way has some different environments within it. So actually the center of our galaxy, right here, it's actually more similar to these early universe galaxies, the environment there, than it is to the rest of the disk of the galaxy. So actually in physical properties, in like its gas temperature and its pressure and all that stuff, it's a lot more like these galaxies than it is like our solar neighborhood right here. So here's a picture of the center of our galaxy. I'm going to talk about this a lot more, so I'll just flash it up here quickly. But about 80% of the dense gas in the Milky Way is in the center of our galaxy. and it has these turbulent velocity fields that are much higher than our solar neighborhood, higher cloud densities, higher temperatures. And so the main point here is that the conditions are really, really different. So we're testing star formation in a really different environment. And the most important part is that I forgot to mention, is that in this plot here, we can't just go and take beautiful images of these galaxies back here. You saw our Hubble field. You can take an image of a whole galaxy, or maybe like 3 pixels across a galaxy. You can't actually look at individual stars forming. So anything that we learn about star formation is in those galaxies is going to involve a lot of assumptions about how many stars form with different masses, how often they form, and stuff like that. And so we'd like to be able to actually watch stars form in an extreme environment. And that's only possible in the center of our galaxy here. Okay, so we're going to look for if there's a rule for star formation, and we're going to look at it in this different environment. So as I said, about 80% of the dense mass mass in the galaxy is in the center of it. So the mass of the clouds are much, much higher, the dense mass. And so we expect the Milky Way center should be up here somewhere. If we just extrapolate this relationship, it's like way up there, just forming so many stars. You can barely even handle it. But it's actually, it's down here, sort of underproducing stars. This may not look like a lot because I didn't put any numbers or axes, but let me just tell you. So this is a log scale. So this is actually, it's forming about 1/10 of the number of stars that it should. So this is a really big problem. This is really breaking that rule, right? So we're going to have to call in our galactic sheriff here to take a look at what's going on at the galactic center. To put this another way, here's a picture of our galactic plane. So thinking about, we saw those pictures of the Milky Way earlier, just Milky Way throughout the sky. This is like a picture of the Milky Way, but now we're looking at a specific star formation tracer, water masers, which trace star formation. So each of these little points is where star formation is currently happening. So because the galactic center has so much dense mass, it should also have so much star formation, according to our laws, right? According to our star formation rule. So you guys wouldn't mind pointing out for me where the super obvious place of lots and lots of star formation is? Anybody? Sort of on the right. We have unanimous confusion. Nobody really knows. So but now I'm going to show a map of the dense gas. So this is the dense gas. Can anyone tell where the center of the galaxy is now? Yes. So it's very obvious. So this is again why we need to call in our galactic sheriff, because this region is really breaking our star formation rules. So going inside the mind of a criminal, here's a picture of our galactic center in visible light. So in the very center here, it doesn't really look like very much exciting is happening there. We probably shouldn't bother looking at that, right? Probably boring. Hopefully you guys disagree, because it's, as I said, this is the optical light where basically all the gas and dust, any really dense stuff is actually going to be blocking out the light behind it. So the really interesting stuff is happening behind that. So if we zoom in into the yellow box here and go to the infrared, you can see, whoa, lots of exciting things are happening now. You can see this huge bubble emanating from the center of the galaxy. You see all these like young or old stars over here, some other bubbles here, some diffuse warm dust just heating up in the space between the stars. And if we zoom in again, this is again showing mostly warm dust. So this is actually the location of Sagittarius star, the supermassive black hole at the center of our galaxy, which is a super interesting topic and would be a great topic for a lecture, but I'm not going to talk about it today. You can ask me later. But that's right here. And then this is a galactic center bubble. This is caused by some really massive clusters of stars that formed in the center of the galaxy here. And these blew out a whole bunch of gas and dust, so they created these bubbles. And then we have more of this dark stuff, which you guys know by now is actually the most interesting stuff. So if we go out to longer wavelengths, this is now showing all that dense gas and dust. So you can see that's where all the cold gas and dust is. That's where all the stuff that might form stars is. So I should say as well that everything in the universe that has a temperature is going to emit radiation. So that means you and me and everybody. Also these tiny little grains of dust in space are also going to emit radiation. But what kind of radiation they emit depends on their temperature. So if you have a really hot electric burning stove, it might turn red because it starts radiating in the visible part of the spectrum when it gets really, really hot. When it gets colder, it would still be lit up, but it'd be in the infrared. So if you were like the predator and you had infrared vision, I could see all of you right now, which I can't really see you, but I would be able to see you in the infrared. And so as you go to longer and longer wavelengths, so visible to infrared to submillimeter to radio, then you start to see colder and colder and colder stuff. If you go the other way to UV and X-rays and gamma rays, you see much more energetic stuff. So we're looking at the stuff that's coldest because that's where the new stars are going to form. So one more picture of the galactic center here. This is now showing, the orange is showing the molecular gas one more time, but now the purple is showing some really long wavelength radio stuff. So this is some ionized gas. So here's the center of the galaxy, which really lights up the Sagittarius star, and you can see these really interesting non-thermal filaments. We really don't know what's going on there. They're very curious features. Seems to be like some magnetic fields and some particles are traveling around the magnetic fields there, but really exotic stuff going on there, just so you can appreciate its full glory. Okay, so as I mentioned, the center of our galaxy is a really extreme environment, and we want to use that to study how star formation happens in this extreme environment. Okay, so we call this region the central molecular zone. It's about the inner 500 parsecs or so. This is a scale bar in light years. That's a lot of light years. That's crazy. And now we're just going to zoom in on one of these clouds here, the center of the galaxy, which we call Bricklet D. There's a whole story. There's like a brick, and then these are like the tiny little bricks, so they're called the bricklets. And now we're looking at the warm dust emission. But again, what you see, most of it is just, it's actually pretty dark, right? Just like it's this gas here. Now I'm going to show you what we see at longer wavelengths in the submillimeter. So this is one of the data. This is actually the first image that we got from the survey that I'm going to talk about in a minute here. So it's a beautiful image, as you can see. And so when I first got it, I was just like, oh my gosh, it worked, because you spent all this time creating a survey and taking data, and you just don't know if it's all going to work. But it did. So I'm just going to show that one more time. So here's the dark cloud, and the mid-infrared is showing warm dust, and it's an extinction. And then here we see, when we go to longer wavelengths, we can actually see where the stars are going to be forming themselves. So to understand star formation in this extreme environment, we're going to use something, a telescope called the Submillimeter Array. The Submillimeter Array is a system of 8 antennas, these ones right here, on the summit of Mauna Kea. This is actually a bad self-portrait. These are my legs right here. This is me taking a picture at sunset on Mauna Kea. I love Mauna Kea. It's one of the coolest places on Earth, I think, so it's really a treat to go observing there. And so we're going to use the Submillimeter Array here to do this legacy survey of the center of our galaxy. So we know we want to go to long wavelengths, because otherwise we're just going to see these optical shadows. We're not going to see anything really good. If we want to see the really good stuff, we have to go to longer wavelengths. So we go to these submillimeter frequencies. And we also know that we need high angular resolution. We want to be able to see individual stars forming, so we can do some of the science that we can in the solar neighborhood. If we just see a big smear, that's not going to be very helpful for understanding how star formation happens. And this is the first survey of the CMZ that's going to do that. So the way that the SMA works is through a process called interferometry, which I'm actually not going to talk about in too much detail. Suffice it to say that basically all of these 8 antennas, they all look at the same thing at the same time, and they act like one bigger telescope. So each antenna is its own individual telescope, and it can look at anything in the sky. And basically the resolution, so how sharp your images are, is related to how big your telescope is. So bigger telescope means better images. So if you have just these little dishes, your images are not going to be that great. But actually, if you take 2 of them, put one over here and one over here, the quality of your images is as if you had a telescope that was as big as this whole distance between them, which is really incredible. You make some sacrifices in other things, but overall, it's a pretty incredible technology. I remember when I was learning about astronomy, it was like the coolest thing ever. So I'm really excited that's what I'm working on right now. Yeah, and I'm not going to talk about the details, how it works. Okay. So as I said, Mauna Kea is one of my favorite places. The photo of the submillimeter array, looking over Mauna Loa, over here. Here's another photo of snow on Mauna Kea. I go to Hawaii for these observing trips, and my parents are like, oh, you're just going to go hang out on the beach? Sounds really tough. And I'm like, no, it's snowing. It's a different kind of beautiful up there. And So I really enjoy going. I'm going to show you a time lapse of the SMA, the Submillimeter Array, at work. So here's 2 of the antennas, actually 3 of them. And you can see the galactic plane is rising at night and that the SMA is following the galactic plane. Here's the galactic center, and the telescopes are following. So this incredible time lapse was from Jason Chu, who I actually found his video on YouTube. And I was like, this is amazing. Can you send me a clip? And he was very happy to provide a clip for me. And he has some really awesome other stuff about some other telescopes on Mauna Kea. So I recommend that you check that out. So I could talk about the SMA and how cool it is all day, but maybe you guys would like me to talk about something else. So here's the survey that we're doing with the SMA. So Christine introduced it as the SMA Legacy Survey of the Central Molecular Zone. Kind of a mouthful. So we decided at some point we needed to have like a shorter name for the survey. So as a leader of the survey, I sent out an email to the team to get suggestions. We had a poll. People came up with some really interesting suggestions. There was Sting, there was CMZ. The most creative one was Beyond CMZ, put a ring on it, which I thought was really cute. But in the end, we decided to go with CMZoom because we're zooming in on the CMZ. Okay, so here's some technical details about the survey, which I assume you guys already understand because you probably read my website already, so I don't need to talk about that at all. This is basically the area that we're going to cover. All of these white contours are looking at the highest column density gas, so the most interesting stuff. For those of you who didn't do your advanced homework and understand what all of this means, basically we've optimized the telescope to find star formation. That's all you need to know. And it's also taking a really long time. It's taking about 500 hours of telescope time, and it's taking about 3 years. So we just began year 3 of the survey, and it's the final year of the survey as well. The huge team of people working on the project, but looking at a big list of names isn't very much fun. So here's a couple of pictures. This is one of our face-to-face group meetings in Germany, actually. One of the coolest things about being an astronomer is getting to meet and work with people from a lot of different countries. So just in this picture, we have people from Germany and India and the Netherlands and the UK, and all of us just coming together because we just love science. We just want to work on it together. And here's a couple of pictures of the different students that I've worked with on the project as well. Silly faces. All right. So CMZoom overall is trying to do a lot of different science topics, and the first one of which, and the only one I'm going to talk about today, is what is the cause of the extremely low star formation efficiency? Basically, why is the center of our galaxy breaking these rules of star formation? And that's what we're trying to understand. So to look at this question, I'm going to zoom in on these 3 little clouds here, right here. So as I said before, this is Sag star, central supermassive black hole. This is Bricklet D, which you saw earlier. And this actually creates this nice little ring of gas. We think the gas is actually moving in streams along this area here. But for right now, I'm just going to zoom in on these 3 clouds here. So this image is showing cold gas and dust in the red, and the green and blue are showing warm gas and dust. So I call these clouds the 3 little pigs, because they kind of look like pigs, especially if you put them in red, but also because their levels of substructure are sort of similar to the fable of the 3 little pigs. So now I've put on contours from the CMZoom survey, here, here, and here, and this is showing us what we detected in the survey. Where is all the cold gas and dust in the CMZ, in these clouds? And you can see that this cloud on the left, it's just really piddly little cloud. It just has like 2 tiny little cores. That's it, that's all that's going on. So this is the cloud that's been made out of straw. It's really not going to last very long. This cloud here, on the other hand, has a decent amount of substructure, but not too much. That's the cloud that's been made out of sticks. And then finally, this one on the right, this one is a real solid cloud. This one is made out of bricks. Okay, so by studying these clouds in a lot of detail, I'm going to put it onto this plot that we looked at before. So this is the number of young stars, and then the mass of your cloud above some certain density. So this is our bricks cloud, the one that's made out of bricks. And so this is where we expect it to be based on its mass. But based on what we're finding, it's actually here or even lower. And so what we're doing with the survey is we're looking at the physical properties of these cores. So what is happening? Is it the turbulence that's making it not form stars? Is it magnetic fields? Is it the temperature? And so our current best hypothesis is actually the turbulent velocity, the fact that these bulk motions in the gas are just stirring things up so much that it can't actually collapse down and form stars. So this turbulent gas pressure is just moving everything around. So in this case, gas pressure, who doesn't want to be hugged at all, is totally winning. It's like, nope, not going to get hugged, and it's not getting hugged. So and this is from the turbulent energy. So we're doing these same kind of analyses on many, many different clouds in the center of the galaxy, and still have a lot of work to do on the survey. But our main conclusion so far is that the gas pressure is winning over gravity. So gas pressure is winning, and the main feature of the gas pressure is the turbulent energy that's keeping it from being able to form stars. So the really big thing that we want to be able to do with this is that now that we've looked at star formation in detail in another environment, can we make a new law for star formation that will actually work throughout the entire universe? So basically, if we add in, besides just the amount of gas at a certain density, but we also add in information about the environment. So what's the turbulent energy? So if you add that in, can you create a real law for star formation? And this would have big implications all over the entire universe, because that would allow us to understand how many stars are going to form in a certain galaxy. So what are the basic rules and principles of star formation? So thank you all so much for your time. And I'm going to show you, wait for a second, riding the SMA from Christy Cunningham as a reward. So thank you very much.
For questions and answers. Yes, ma'am.
Okay, so I have two different questions. They're kind of the same, but they're both two parts. So the first question is, like, in our solar kind of neighborhood, what's the maximum and minimum estimated amount of time of like stars forming if there was a nebula?
That's a good question. So you mean like from when the gas cloud, it depends on when you start, right? Because there's no like t=0. There's no just starting clock. You're like, press your stopwatch. Okay, ready, go, start forming stars. So basically from the time you get like these dense clumps to the time you actually have a star is, like I said, about an order of a million years, but that depends on the mass of the star. So really, really massive stars, the really biggest ones, they actually form really, really quickly. And then the lower mass of stars, like really lazy and lethargic, and it just takes a really long time. So that can be like maybe 5 million years or so.
And my second question is, with the center of our galaxy, what's the maximum minimum for that one?
We don't know that yet. It's a great question. Do you know? Yeah, good question.
Yes, sir?
Yes, I don't know if I saw it in an astronomy magazine or something, or I heard it somewhere, maybe at one of these lectures, but isn't there about 3 or 4 stars that are kind of very close to us, that they believe we were kind of like closer to them 4.5 billion years ago when we formed? Is that really something that my mind made up? Or, yeah.
I'm not sure. That's not something that I've heard, but I do know that stars, they move, and so basically speed is relative. So we think that we're standing still, but on the Earth is actually moving really, really quickly around the sun, and the sun is moving really quickly around the center of the galaxy. So stars are always moving. So it's very possible that our star was somewhere else.
Yeah, somewhere I heard that there was like 3 or 4 stars.
Maybe, yeah, I'm not
Because
sure.
there is so many stars.
Yep.
Thank you very much.
Yep.
There's a young fellow right up front. Hi.
Hi. So I was wondering, I was surprised that you didn't talk really much about the black hole at the center of our galaxy,
Yeah.
considering it's such a big part of it.
Yep.
I'm wondering, you explained pretty well why stars were having trouble forming. I was wondering if any of that could be possibly traced back to the black hole, like maybe it's more turbulent there because the black hole is spinning really fast.
Yeah, so it's part of what's going on. So it's not just the black hole itself, but it's the fact that all the matter in the galaxy is just sort of a bunch of gases like falling into the center of the galaxy, and so that causes a lot of this turbulence. And as a reward, I actually have a video. So this is the black hole here, and these are individual stars. And so this is over a long period of time following the motion of stars, and this is why we think that there's a supermassive black hole there. Because you can't see the black hole, but you can see that the stars, they have these weird orbits. Like, why is it bouncing back over there? Like I said, I wanted to talk about the black hole because it's super interesting. We don't think it has direct effect on the gas clouds that we're looking at, but the fact that it's at the center of the galaxy and like stuff is funneling in there probably does have something to do with the turbulence that we see. So it's all related. Yeah.
Oh, thanks.
Yep.
That was a great question. Gentleman back here, and then we'll move up here.
I was wondering, what's it like at the moment when fusion begins? A star forms, how do you define that moment when fusion is really starting and it's starting to shine?
Yeah, so it's, I don't know about the exact moment, but shortly afterwards it becomes fairly obvious. So you start to see really, really bright radiation because fusion is a really, really good source of energy. You actually are taking some of the mass, so you have two objects that are going together, and when they collide, the combined product has less mass than the two separate. And if you think about Einstein's equation, E equals mc squared, c, the speed of light, is like a giant number. And then if you square that number, the mass that you're losing is getting turned into energy. It's a huge amount of energy. So it's basically just the radiation from the star that we see. And we're like, okay, stars are forming. Yeah.
Right there, second row.
So I guess my question was about a similar thing, but kind of trying to understand the time scale of like when the dust actually becomes like a star. Is it very gradual, or is it sort of like something that suddenly ignites and suddenly there's a star there?
That's a good question. I wonder if there's other astronomers in the audience might know. I think it could be fairly quick because basically the temperature has to get up to a high enough. So it's going to be a statistical process anyway, so you just have these particles just whizzing around, right? So they're just going to keep whizzing around, and then eventually they get fast enough that there's going to be a chance that they collide. And so it might not happen all right at once, but once the temperature is high enough that it can happen, it's probably going to keep happening.
So just really quick, is it like would you say it's relatively quickly? Like, is it like over a course of like 1,000 years, or is it like really quick?
I'm not sure of the answer to that
Okay.
question, so I don't want to say,
Yeah.
I'm sorry, I don't know, yeah. Yep.
Any questions up in the balcony? Ah, yes, in the back.
Hi.
You had said that stars haven't been forming as much as they used to.
Yep.
And that's because of turbulent energy, is that correct?
So it's different. So basically, stars in the early universe, there was a much higher density, so things were much closer. So you had a lot more stars forming then. And the reason that the center of our galaxy is forming less is because of the turbulent energy. But yeah.
Is there something causing that turbulent energy?
So it's similar to this gentleman's question in the front.
okay.
So it's all about basically as the gas is falling into the center of the galaxy. So our galaxy has a bar and it moves. And basically, as material hits that bar, it can actually cause friction. That friction causes it to lose energy and it starts falling into the center of the galaxy. And as it comes in, it carries with it a lot of gravitational energy. And that gravitational energy gets turned into this bulk motion of turbulence. So specific to the center of our galaxy. Yep.
Oh, one hand, yes, right here.
How do you measure the mass and density of a molecular cloud?
Good question. So I said molecular clouds are made mostly of molecular hydrogen and carbon monoxide and also dust. So two main ways that we can use it is we can use the emission of carbon monoxide. We can basically look at how much light it's producing, and then we know something about the molecule of carbon dioxide and how it emits light. And so you can reconstruct how much mass there must have been to create that much light. Or we can use the dust itself. So dust radiates like a black body, like the sun, or like us, we radiate like a black body. And so we can actually just look at how much emission is coming from the dust, how much light is coming from the dust, and use that to infer how much mass there is.
And yes, ma'am.
Is the sun, when you show those pictures of the sun, it looks like it's actually is a ball of something, but is it something that's substantive the way that the Earth is, but like a burning version of it? Does the dust glue together to form like a core of iron or any kind of thing that's actually solid?
Yeah, so there's nothing solid in the sun. It's all like gas, right? So it's similar to Jupiter actually. So if we think about Jupiter and how it might be cool to visit Jupiter, but actually if you visited Jupiter, you just start falling through the atmosphere and it would just get slightly more and more dense and maybe be really cloudy, but you'd never hit a surface. And the sun is similar, although it'd probably be a lot hotter. But there's no surface, no standing.
Anything that you would bump
Yep,
into.
that's right. It's all this plasma, so it's really hot gas that's totally ionized. Yeah.
Okay, let's do, you actually had your hand up earlier. I'm going to do one final question and then wrap up, so this gentleman, please.
What determines the size of the star that's formed? I mean, they come in various sizes, I guess. So how is that determined? I would think once fusion gets going, blows away the other gases, that's it. but apparently there's some variation there, so what
Yeah.
causes that?
This is such a profound question. So the question was about what determines the mass of the stars. There's actually another large survey going on with the SMA that's all about understanding this question, because we really don't know. We have some ideas, but we really don't know, because we think that it might be basically if you have a whole big cluster of stars, that the whole potential of the entire cluster is like there's so much gravity right in the middle. So if you happen to be one of the cores that's right in the middle, a lot of material is going to funnel onto that. So that's one idea, that basically your environment, your location can determine the mass. There's so many variables, it's hard to say. Yeah.
All right, and with that, we're going to conclude the formal portion of our observatory night. I want to thank all of you who are watching online and here in person for joining us tonight, and hope that you'll be back next month. Thank you.